going to do something a teeny bit different today. I am going to put up on the blackboard, and you are going to reproduce on a piece of paper the basic concept map, a map of the ideas for thermodynamics. So what I'm going to show you is a concept map of what we've been doing the past few days. So I'll call this a thermodynamics concept map. Okay. So that's what we're going to do. All right, so what is some of the key ideas? It starts with the first law, which is that the change in energy can come from two sources, work or energy due to heating or cooling. Then we have the second law, which says that delta S is greater than or equal to 0 in a closed, isolated system. And we worked out what W was. W is equal to minus the integral of P dV, and that comes from mechanics. So that's a basic result that we get from classical mechanics. That's how we derived that. Then these two things, the first law and the second law, lead to a definition, motivate a definition for temperature. And that definition is 1 over T is equal to the change in S over the change in E at constant volume and number of particles. All right, so far that's the logic that we have used. All right, then this implies the following result, which is absolutely astounding, that the change in entropy is equal to Q over T. And this is valid for small q or constant T. I mean, it's not even clear what it would mean if T was not constant. And obviously a quasi-static process. And this means quasi-static means you go through equilibrium states. Usually that means you do the process slowly. All right? But you're going from one equilibrium state to another. Now we have a definition that the heat capacity is delta Q over delta T, and I put a third line there for definition, and this is heat capacity. We have that. All right? And from this, we can get a few results. We can integrate to get the energy due to heating cooling is C dt, like that. And then for certain, in a constant volume situation, we have delta E equals the integral CV dt, constant volume. And that's because work equals 0 in a constant volume and the first law. All right? So due to the first law and W equals 0, we can say this. All right. Now these two things, this and this, lead to the result that delta S is equal to the integral of C dt over T. All right? All I'm doing is integrating this, replacing Q by the dQ by C dt. All right? So it gets from that. And then we can add in the third law, which says S at 0 equals 0. So S at t equals 0 is 0. And then this implies S of t is the integral from 0 to t. And then we just put in for C. C can depend on temperature over t prime. And this t prime here is simply an integration variable. So this is the concept map. It has all the ideas. I'm going to just put in a few things here. Let's do the ideal gas. In order to use this, we need a few things. All right? And this comes from either experiment or kinetic theory. All right? So you can get it from either of those. And here's some of the ideas that you should know. NKT, or in other units, nRT. That's the pressure. The energy is equal to 3/2 NKT, or 3/2 nRT, for a monatomic gas, which means the molecules have one atom in them. Okay? More generally, E is just 1 over this gamma minus 1 NKT, or 1 over gamma minus 1 nRT, where gamma equals Cp over Cv. So we have that result. And we have a couple other results. We know Cp minus Cv equals Nk, or Nr, depending on the units you use. And we have this result, Pv to the gamma equals a constant for a quasi-static process. Quasi-static and adiabatic. All right, that's Q equals 0. All right. All these are equilibrium results. All of this has to do with equilibrium. All right? Only if the system goes from one equilibrium state to another does it make sense to even do these integrals. All right? Because otherwise, if you don't go from one equilibrium state to another, these things aren't well defined. All right? So it's only for equilibrium states. And then one last result we have for solids. We know that Cv equals 3 Nk, or 3 Nr. All right. We have something called state variables. Here are the examples that we know of. What are they? E, V, N, P, T, S. All right, those are the state variables. We have extensive variables. These are the ones that depend on how much of the system you have. And those are E, V, N, S, and the heat capacity, C. That's also extensive. And then we have intensive. All right, we have P, T, and then the specific heat. This is specific heat. And we can also have the density, rho. So that's density. Those are examples of intensive variables. All righty. So that's what the ideas are over the past few days. And then you have to, in order to solve any problem, you have to use this logic. You can't just write formulas down. You have to use the logic. You have to use words. You have to say it's the first law. It's the second law. It's a quasi-static process. All right? It's adiabatic. You have to use words to be able to make conclusions about using those formulas. Under what circumstances are they valid? And we have those listed here. Okay. All right. So one thing to remember, almost all these formulas up here are only for thermodynamic processes, where you're going from one equilibrium state to another. You can't even define many of the quantities here out of equilibrium. And the quiz problem is clearly not a thermodynamic process. It's not quasi-static. So for instance, the first question, does the energy change? Well, the system's a closed system. The gas is in the container and in the box. If the energy is going to change, that energy's got to come from somewhere. Where did it come from? Where did it come from? Just out of the blue sky? The sky's not in the problem, so it can't even come from the blue sky. That's an English expression. All right. So there's no way the energy can change, because it's a closed system. Is it doing work? Is the gas doing work? Well, you might say, yeah, look, the volume's changing. There's some pressure, so there's work done. But what's it doing work on? There's nothing to do work on. The gas is expanding into a vacuum. There's nothing to do work on. So the gas expands, but not because it's doing work on something. So W is 0. Q is 0 because there's no energy going in or out of the system. It's not being heated up. I didn't say there's some kind of candle there or a Bunsen burner or whatever heating this thing up. Nothing. All right, so the energy doesn't change. Q and W is 0. But what does change? The entropy has to change. There's no way the entropy could stay the same. That's by the second law. We have a closed, isolated system. The entropy has to either increase or stay the same. It can't stay the same because it's not in the same state. It's in a different state, different volume, different pressure at the end. It's different. So the entropy has to change. All right. And then you can go through the rest of the quiz and make some arguments about it. So what we're going to do today is discuss what historically, in terms of the development of this subject, was extremely important, and it's still important today. And that's the concept of heat engines. To really understand the energy crisis, actually there is no energy crisis. We have plenty of energy. There's enough energy if I converted your body into, was able to convert it into pure energy using Einstein's E equals mc squared, I could power probably the whole city of Hsinchu. All right? There's plenty of energy around. The problem is we can't get that energy to do work. And that's where thermodynamics comes in. So we don't have an energy crisis, we have an entropy crisis. Too much of our energy goes into entropy and not enough into work. All right, so let's see how that works. The key idea of all heat engines is you want to go in a cycle. And at the end of that cycle, you're back to where you started from, but you've done some work. All right, so usually the way it works is we have a hot reservoir, we have a cold reservoir. All right, the hot reservoir is at T equals TH. The cold reservoir is T equals TC. And then the system goes around like that, and then there's work done. All right? So the system goes around in a cycle like this. Okay, it comes back to the hot reservoir. There's QH. And I'm going to use absolute value signs, so we don't have to worry about positive and negatives. There's energy, QH, absolute value, QH, positive energy going into the system. So here's our system. And then there's energy, QC, leaving the system, and some work being done. So you have QH is used, this energy that's taken out of the hot reservoir. That's why you have coal or nuclear reactors or whatever you have, you're heating up your system. And that energy that gets heated up, some of it goes to work, turns some kind of turbine to do work, and then some of it is lost into the environment, usually some cold reservoir. That's why power plants are usually near bodies of water, because that water helps to maintain a colder reservoir, and that's important. All right, so from the first law, we have QH is going into W plus QC. All right, so that's the first law. From the second law, we have delta S is greater than or equal to 0. Okay, but what is delta S? So delta S is equal to, well, so we want to know the change in entropy of the system. All right? So we have QH going into the system. So the entropy of the system is increasing, right? We're putting energy into the system. So by this, QH is going in, T is constant. Okay, so we can use that. So delta S is QH divided by TH. All right? Because our system here is kept at this hot temperature, and the energy is flowing into it. All right? Then here, the energy is flowing out at the cold reservoir. So we have minus QC over TC. And this has to be greater than or equal to 0. All right, so we use the first and second law of thermodynamics. All right, so we wanted to know how good we've done. How good is this? All right, so let's figure it out. We have to figure out the efficiency of the engine. Efficiency. So the efficiency E, it's equal to what you got divided by what you put in. So what do we want to get out of this engine? What do we want? Work. We want to get that W out of it. And what do we put in? What are we using that coal to do? What are we using nuclear reactors to do? What do we use oil or whatever? It's to heat up that gas. And so this is what we put in. Right? That's what costs money. All right? That's what we get oil from the Middle East or coal from wherever. Do they do coal in Taiwan? You have some nuclear power plants. What else do we have here? Do we have coal? Where do they get the coal from? Are there mountains where they can get coal? They buy it from somewhere else? Okay, wherever. Costs money. All right, so let's put this in. This is W. And then we have QH. Now let's replace W by what it equals. Over there it equals QH minus QC divided by QH. All right. So that's equal to 1 minus QC over QH. All right. Now from here, all right, from the second law, we see that QH over QC is greater than or equal to TH over TC. All right? So QH over QC is greater than or equal to that. So QC over QH is less than TC over TH. All right? So this is less than or equal to 1 minus TC over TH. The efficiency that is less than 1 minus TC over TH. Okay, all the temperatures are in Kelvin. Because QC over QH, if I bring it over here, that'll be less than or equal to TC over TH. So if it equals TC over TH, that's the best you can do. And if it's less than, it'll be there. So you can never have a 100% efficient heat engine. You can't do it. Maybe another way of thinking about it is TC over TH, this is always greater than this. All right? So this is always greater than this. So that means E is always going to be less than this number. So how do we get the best engine possible? All right? So what's the best engine we could do? So the best engine would be delta S equals 0. That's the best you could do. So that would be a reversible case where QH over TH is equal to QC over TC. That's the best you could do. And that implies that the maximum efficiency is 1 minus TC over TH. That's the best you could do. So what that implies is that you try to make the difference in temperatures. You try to make TH much, much hotter than TC. That's why you use nuclear power and coal, and you try and heat that fluid up, whatever it is that's going to heat the gas up, the reservoir, you keep that as hot as you can, because that's going to give you the best efficiency. That's why car engines have hot engines, right? You're not going to get very efficient using this kind of engine by having the two temperatures be the same. So for example, a lot of people have suggested, well, why don't we use the oceans? Because the top of the ocean is hotter than the bottom. So there's a temperature difference. Why don't we just run gas through that? Well, that's very inefficient because the temperature change is not that big. And secondly, we have to do all this work to move the gas around. So we're not going to get very far using that. All right. Now, surprisingly, in the 18th century, 1800s rather, I think it was the 1800s, maybe the late 1700s, a French physicist, Carnot, figured out how to get that best engine. Of course, he had to have a perfect engine to do it. There are all kinds of losses that are not even covered by thermodynamics, right? Friction and all kinds of things going on. But he figured out, in principle, how to do this best engine. And this is what he did. So I'll do it on a PV diagram. All right. There are 4 steps. You take your system around. All right. So the first thing you do is first take something, an isothermal expansion. So you expand it isothermally. So you go like this, and this is isothermal. So it's like that, and that gives you your QH over TH. That's the delta S in that part. Okay, so you do an isothermal expansion. Then you allow the system to relax doing a adiabatic expansion. So it expands a little more, but adiabatically. So you go down a little bit like that, and this is adiabatic. All right, so that means Q equals 0. All right? Then you come up and do an isothermal contraction. All right, and you have QC over TC is delta S there. We'll call this delta SH, delta SC. And then finally, you do another adiabatic, and you get Q equals 0. All right, so that process will give you the maximum. So you have delta S here is 0. This is a adiabatic quasi-static process. And then over here, we also have delta S equals. So the total delta S is equal to, just like anything, just like before, this plus this minus this. So that's the total entropy change. Okay. Since we go through and come back to the original situation, so we go here, 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 here. So we come back to the original state. That means that delta S is 0. Okay? So we get 0 here. All right? And then we get the maximum efficiency. Okay? So that's how it works. If you wanted to check it with the ideal gas, you can do it. You can see for the isothermal expansion here, you'll get a delta S over here. We can figure out what's going on here, how much work is being done doing these processes, and we can work it out. All right, I'm not going to do that. I'm going to leave that as an exercise for you. All right, so we're going to talk briefly about refrigerator. Refrigerator, which is basically the same as an air conditioner, right? Which is a cooler, something that cools down a certain volume. Okay? What a refrigerator is, it's a heat engine in reverse. That's all it is. So you have your system. You do work on the system. It puts out energy, all right? And it puts out energy, and that's what cools it down. But we have some energy going in. So it's the same kind of thing, but it goes the reverse. Where does that energy go? Let's say you have a refrigerator in your room. Where's that energy going? What's the hot reservoir? What's the cold reservoir? What's the system? Anyone know? Anyone ever look at a refrigerator? What's it made of? Anyone ever look at the back of a refrigerator? I think they still have you see it in the back. What do you see in the back? Anyone? You're not very curious. You're engineers? And you're or physicists, right? Both of you should be curious about this. All right. Well, I don't know how they look nowadays, but in the back of a refrigerator, you have a bunch of tubes. And if you put your hand on those tubes, you might burn your hand because there's fluid flowing in those tubes. And that fluid is relatively hot, and it heats the room up. So it can cool the inside of the refrigerator. All right? So the cold reservoir is inside the refrigerator. I'll write fridge, abbreviation. The hot reservoir is your room. And the system is there's some kind of coolant, they call it. It's some fluid. And one of the things they've tried to do is change the nature of that fluid, because the fluid they used to use was bad for the environment. And sometimes it leaked out, and that was bad. So now they banned some of those fluids. All right, so you basically have the same thing. W plus QC equals QH. All right? Yeah, it's the same as up there. Same kind of thing. All right? Because you have this going in, this going in, that going out. All right? Okay. And then we have what's called the coefficient of performance. Coefficient. And you'll see in a minute why efficiency is not the right thing. All right. All right, so what do we want? What do we get out of this is we want QC to come out, and W is the work we do. So this is QC over W. And then we can replace W by what it equals. So we get QH minus QC, and then QC up here. We divide through by QC, you get 1 over QH over QC minus 1. Okay, that's right. The only thing I forgot is to put the absolute value signs on. All right? So that's what you get. And then just like before, if you make the entropy, the total entropy 0, you can replace the Q's by T, and you get the best is 1 over TH over TC minus 1. So that coefficient of performance can be as large as you want. Because I can make TH equal to TC, and I get 1 minus 1 is 0. 1 over 0 is infinity. Boy, that's a great refrigerator, you say. It's got a performance that's infinite. Well, it's easy to make it infinite if the room temperature and the temperature inside the refrigerator are the same. So if I take my refrigerator, unfortunately you can't do this in Taiwan, but I could do it in Michigan. I could take my refrigerator, put it outside, and it'll be great in the winter. Right? Because the outside temperature is what I want the refrigerator to be. It might even be colder. So my refrigerator doesn't even have to be plugged in. It'll work. Okay? So that's the best you could do. All right, so that's how a refrigerator works. Same thing for an air conditioner. All right, air conditioner is the same idea. The difference for an air conditioner, which is why it's very interesting in Taiwan, you really see these air conditioners in practice because they're basically what are called heat pumps. You see all those fans on the outside, right, of buildings? They're all over every building. You never see that in the United States. Never. They hide the air conditioner, these things. They hide it somewhere. But here, it's right there. You can see it for every room, practically. There's this little fan thing. And why is that? Because when they're using it to cool the room, all right, then the environment, the outside, is where it's hot. And so they're trying to put heat out into the outside. And TH is actually big, relatively big, compared to TC. And so you don't get, this is the best you could do. All right? There's all kinds of other inefficiencies going on that make it not work quite as well. You can run your refrigerator in reverse. You could pretend, right, that the inside is in the outside and the outside is the inside, all right? And you get a coefficient of performance for the heater part. So running fridge in reverse, you get COP for heating. This is for cooling. So if you run it in the other way for heating, you can just work out the analysis. It's the same idea. You get 1 over 1 minus TC over TH. So this is heating the best you could do. Okay? All right, so you're trying to heat it up. All right, so you'll get a little less than, you always get less than. Again, you can get infinite because if your temperatures are the same, it works very well. So my understanding is that in Taiwan, you know, all those, we don't have one. You know, if you go into a room like my apartment or a lot of the rooms, you have one device that does both heating and cooling. And that's called a heat pump. So that's a heat pump that does both heating and cooling. So heat pumps work very well in an environment like Taiwan where it doesn't get too cold. You'll never, never, ever see a heat pump in Michigan where I live. It's too cold in the winter. Heat pumps are not very good. They just can't heat up the place because it's too cold in order to use. You need a better approach. You need a furnace, all right? And you heat it up. You burn either oil, nowadays it's oil, or gas usually, natural gas. They burn that, and that heats up the room. And again, remember, when you heat up a room, you're not actually adding energy to the room. You're really kicking out particles that have low energy, and they get thrown out into the environment. Okay. So this is a very important thing. So the key here is you cannot, so if there's one lesson you want to get out of this is you cannot convert all of the energy that you extract from anything, coal, oil, whatever, 100% into work. right? And in our economy, that usually means you cannot extract all the energy into electrical work, electricity. You're going to lose some, no matter how good a machine you have. If you eliminate all sources of friction, etc., you're still going to lose out because of thermodynamics. There's no way of doing that. There's no way of having a perpetual motion machine that goes around and around and converts energy to work perfectly. That's impossible. All right? People have tried who didn't know any thermodynamics, and it's always fake. There's always something wrong with their machine. There's some source of energy that they either are trying to cover up, right, because they're trying to sell this thing, or they just didn't understand. They didn't realize there was some source of energy going in to the device. Okay. Let me just give you a little preview of what we're going to do this coming Thursday. So this coming Thursday, we're going to talk about a different topic called statistical mechanics. And the key to this is this idea. All right. We're going to build models. Actually, we're not going to do much of that, but if I was teaching a regular statistical mechanics course, we would look at lots of models of matter, microscopic models. How do the particles interact with each other? And the key thing that you want to do is to describe two kinds of states. We have microstates and macrostates. And statistical mechanics gives you the connection. Microstates, macrostates. All right? In thermodynamics, we only look at macrostates. This is like the total energy, the volume, the pressure, the temperature, things like that, entropy. Let me put in entropy there too. All right? Those are macrostates. What's a microstate? All right. A microstate, let's say for a gas, would be, one microstate would be saying what every single particle's location and velocity is. So that means I'd have to make a list, 10 to the 23 times 6 numbers, right? 10 to each particle, and say what its position is, its x position, y position, z position, and the same thing for velocity. And when I make that list, that is one microstate. I change one particle a little bit, that's another microstate. I change its velocity a little bit, that's another microstate. So I have a lot of microstates. The particles in this room go through billions and billions and billions of microstates. But they're all just one macrostate. It all has pretty much the same energy, volume, number of particles, etc. All right? Statistical mechanics makes a connection between these two. And the connection is this. For a closed system, the entropy is said to be Boltzmann's constants times the log of this, which is the number of these guys that the system can be in. Somehow, we actually can count how many microstates there are. And if I count that, then the entropy is given by k times the log of that number. And we use a log for two reasons. One, this number is astronomical, really big. So in order to make it smaller, we use a log, right? Because the log of, let's say, 1 billion And base 10 is only, what, 9. That's not too bad. Right? And we're going to have many billions. So the log is needed. The other reason is that if I have two systems, I have a bunch of microstates over here and a bunch of microstates over here, I want the entropy for the sum to be the sum of the two entropies. Well, if I have X microstates here and Y microstates here, the total number of microstates is xy, and the log of xy is log x plus log y. So that makes sure that the entropy is extensive in the way we want. Okay. So we will start with this on Thursday, and then we will develop. We won't do many calculations because we can't really, but I want to show you one very important result, which is what's called the Boltzmann distribution. And from that, we can get a lot of other results. And that's what we'll do on Thursday.